I work for Tarka Labs. I have over 17 years experience, and I'm a polyglot, and I like. So I'm a programming language sort of a nerd. So I like playing around with programming languages, and there is often a lot to learn. And Rust has been a very nice learning experience overall. I think we've been dabbling with Rust past 2 3 years, I think now, and we learned a lot. And so yeah, I'll attempt basically to walk you through and show you okay why Rust is popular and why Rust has certain advantages. And then yeah, we'll understand Rust a little bit better, and then that would help us getting started with actually learning it, and then probably followed up by Vagmi's workshop, you will have a very good understanding of Rust today. Okay. So yeah, brief introduction. Yeah, so Rust has topped the charts as one of the most desired and admired programming languages in most uh, surveys, specifically the Stack Overflow's annual developer survey, and this is something kind of a big deal. And we would basically how the criteria that they look at is basic that they survey the people, and they ask them, okay, given that they are working in something, how likely are they to continue working on it in the subsequent years, the next year. And so with Rust, it's like with more than 80% developers, they say that I want to continue working with it, and that is sort of treated as an indicator that is admired and desired programming language. And to contrast it, I think one of the least desired programming language is MATLAB, where only roughly about 20% developers who worked with MATLAB say I want to continue working with it the next year. And yeah, I think that was a nice tidbit to know. And so yeah, today we'll try to see um, why and what of Rust. So this will be the agenda, this overall roughly. So we'll talk about what is Rust. We'll talk about why Rust, why to use Rust, why Rust is good, and following that basically with what are the key features of Rust that make it good. And then we'll go over a little bit of how to get started with Rust, what is the basic syntax or to do basic the programming syntax, the language. We'll talk about the ecosystem and what community there is a little bit, and then I'll also share a few resources which people can utilize. Um, okay. And yeah, I would say, feel free if there are any questions. I think we can probably, raise a hand, and we can, we don't have to wait till the very end. We feel free if there are any specific questions or something that is not maybe clear or whatever. Feel free to ask them, and then I'll try to answer them. Um, Bearing in mind we have some time constraints, so yeah, let's see. Okay. So what is Rust? Yeah, so it's a programming language that was developed by Mozilla. It was first released in 2010. I mean, it probably was in under development much longer than that, but it was first released in 2010, and then in May 2015 is when they released their 1.0 sort of the stable release. Ever since that, basically, there's been a lot of uptake with Rust. A lot of people have been intrigued by it, and they've been using it, and then it's sort of become mainstream now. They've been able to also get it as a first class citizen in Linux kernel development and a lot of other areas. And so originally, basically, it was designed for performance, reliability, productivity, specifically developer productivity and safety. And obviously over the course of the presentation, we will understand how really these aspects shine when we use Rust. And to go about it, okay, so Rust is basically a statically typed systems programming language. So statically typed means all the expressions and variables, stuff that we defined, the types of those are determined at compile time itself. So nothing is left to it at runtime. So at compile time itself, they're both determined and checked. So we just to say, okay, the compiler will return you errors and stuff in case there's been some kind of type mismatch where you declare something as something, but then you try to assign it to some other type and things like that. So at compile time, everything is known. Nothing is left to runtime when it comes to types. And all of this basically does help in memory safety and error detection, because at compile time we are able to. But that is not necessarily unique to Rust, because that is a trait of any compiled language. However, as we'll see in more detail, Rust is able to leverage this and a few other design principles that have gone into the programming language to really give you memory safety in a sense that no other language has given us before. Now, obviously, there are other languages that try to take ideas from Rust, um, and have similar behaviors. However, I think Rust probably was the first one to champion this in a unique way. So why Rust? Okay, let's talk a little bit about that. Rust offers basically a unique combination of features, which again we'll see in detail, which help solve some of the developers' most frustrating, memory management problems. So now when we sorry, okay, I was getting a call. Yeah. Yeah, so I mean, so when we speak about programming languages, at the end of the day, whenever we are declaring certain things, so we have to allocate memory. A lot of different languages take very different approaches on exactly how memory allocation and basically memory management is done. And so if we compare and contrast it with something like C++, where the developer has the responsibility to both allocate as well as free memory. But if you compare that with some other programming language such as maybe Go, or for the matter of fact any language that has sort of like a garbage collector, there the idea is, okay, you can go on allocate as much memory as you need throughout the course of your program's lifetime. However, there is in the programming languages runtime, it has a garbage collector which would at various stages during the execution of your program will kick in and then look at all the memory that was allocated that is no longer reference, and it will clear that up. But of course that comes at a little bit of a runtime cost. There's a penalty that you pay for it. And now Rust takes a very different approach here. So Rust is a different approach because it does not have a garbage collector, which is to say that it tries to um, very cleanly um, define, okay, how memory is going to be allocated as well as freed. But all of this is uh, done at the compile time, so we are able to make sure during the compilation stage itself that we have a very very strong um, uh, idea about when memory is going to be allocated, when it will be deallocated, or rather freed up. And so as a result, a lot of these issues are mitigated. And so because of this, obviously, it is ideal for systems programming, for embedded systems, and much more. And so this is why the early adoption had been in that space. And so some of the key advantages of which we will look into much more detail for us are memory safety. So I've already dabbled into it a little bit, but we'll look into much detail. Then this idea of zero cost abstraction, which is again a very very interesting and very nice thing that Rust provides in a very big way. And then of course concurrency, where also they coined the term sort of fearless concurrency, where the idea being, as a developer you can write concurrent programs without having to worry a lot about the problems and bugs that are associated with writing concurrent programs. So memory safety. So I mean, yeah, this is a sort of a big topic, but we'll try to.
Dhruva, we lost your audio. Oh, okay. Okay, we'll give a minute. I think he got a call. We try to avoid that. I think they continuously called him, so that maybe there's something emergency.
Hello. Yeah, sorry guys. I think I was getting a call. I've just given up my phone. So we look at the memory safety in a big detail, in bit more detail now. So memory safety issues are one of the more leading causes of security vulnerabilities in computer systems, especially embedded systems. And especially when we consider system programming or low level programming, the idea is, okay, you manage memory, and then of course the most of the issues that are associated with is either you are referencing memory that has been deallocated already, so which is sort of a dangling reference or an invalid reference, or what you're referring to has been written to by somebody else. And so those are the kind of basic issues that do crop up in, especially when it comes to memory safety. So now, how does Rust tackle this up is what we will look at. And right. And so in a memory safe programming environment, the idea is basically it gives you constructs that will basically make it very difficult, or rather almost impossible, to actually make such issues. So for instance, is Rust is designed so that it is impossible for you to access unintended memory, where you would somehow be accessing memory that is written to by some other process or something outside of the scope of your program. So the Rust compiler toolchain ensures that at compile time we know exactly, and so of course this is not a possibility. So there is no way to do that. And so there are various features that are included in the language, which all tie together to provide you memory safety, right? So the main thing, the first thing is mutability. Now by default, whenever you declare a variable, whenever you allocate memory, it is read only by default, which is to say, you cannot actually make changes to that. You cannot mutate it, right? However, when you do intend to, let's say, work with certain things that you want to mutate, which is the allocated memory on the heap, then you have to explicitly declare those variables as mutable, and only then will you get the ability to actually modify what is there. And even then, of course, there are a set of rules and stuff which again will look, which control how and what you can do with it, right? So for one very basic example is that you can only have a single reference at one time. So basically, given that you have allocated memory, and it could be anything, given you have allocated memory and you are having a reference to that as a pointer, but then you can only have one reference at a time. And so the next big thing is ownership. So Rust has a very, this in itself is a very big topic in general, but then, it's basically, you can think of it as a set of rules that Rust has that govern exactly who gets to own a certain piece of data. And then obviously, because of the rules, the compiler will ensure that, undesired or invalid behavior, it does not creep into your system, right? So all programs have to manage the way that they use a computer's memory while running, right? This is something that is not unique to Rust, but in some languages, like I was describing earlier, right, in some languages we have an approach where, okay, you have a garbage collector that will do the job of freeing up memory. But in Rust, we have and the other approach is also that the programmer explicitly, like for example, in the old C++ days, so you allocate memory, but then again, it is your responsibility to free that up. But now in Rust, we have sort of this third approach where, okay, memory is managed through a system of ownerships with a set of rules that the compiler checks at compile time. And this is very important, or rather, it's a kind of a paradigm shift altogether, because at compile time itself, we have a very clear idea in terms of the memory, when it is allocated, when it is referenced, when it is mutated, and when it no longer is valid, basically, that it has to be freed, right? And the idea is, if any of these rules are violated, we would know it at compile time itself, not at runtime. So at compilation, when you're actually just compiling your program, at that instant itself, you would know if there are any violations to these rules. That would end up basically creating bugs in your code, right? So we are preventing a lot of these memory management issues at compilation time itself. So what are the ownership rules? Okay, so again, briefly, we'll talk about that. And so for example, each value in Rust that you declare would have an owner, and they can only be one owner at a time, right? And when the owner goes out of scope, the value will be dropped, which is to say that that memory is going to be freed, no longer will be considered something that has been allocated, right? And again, I won't talk about garbage collector. I think we've already spoken about that already. But Rust, the way it does it, at compile time itself, we will know. And so once it's out of anything that has been referenced that is out of scope, it will be marked as something that is been dropped. Okay. Yeah, I mean, so this is fine. So now again, so here the Rust approach is that the memory is automatically returned once the variable that owns it goes out of scope. So I think that is pretty straightforward. But then uh, all of these rules, along with the compiler checks and stuff, kind of make sure that we are working towards it. It is not just the responsibility of the developer anymore. The compiler is ensuring that. And so it again it that's why developer productivity is usually very good, because one, you are not paying the penalty by having a huge garbage collector that comes in at your runtime, eats your CPU cycles to do stuff, right? We no longer have that, but at the same time, it is not my responsibility to free up that memory. And obviously there are a lot of issues that are related with it. You might forget freeing up memory or free up memory too early, things like that, right? So we are avoiding all of those things because the compiler is keeping track of all of those allocations and when they are going out of scope during compile time itself. So with ownership, we also have this whole that the next concept that comes in is sort of the concept of borrowing. Now, so the action of creating a reference is called basically borrowing. So when you create a reference to any data memory that has been allocated, when you create a reference to it, that's basically considered as borrowing. And so I mean, this is just like in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. So this is basically the philosophy, right? Simple philosophy behind this concept. And the idea is this eliminates the whole concept of dangling pointers and creates a mechanism like a read write lock. So only the person who has access, one person only has access to the reference, who owns that basically at a time. And so there is no sort of um, simultaneous writes happening at all. That's not even allowed. And so you basically automatically get sort of like a read write lock where only, okay, one person is allowed to write only at a time, and only one person has that ownership, right? Two people cannot have ownership of the same thing. And so just as variables are immutable by default, so are the references. So when you create a reference to an allocated memory, by default, it is immutable. However, and so we are not, and by immutable, which means is we are not allowed to modify that. However, you can create mutable references as well. But again, then there are rules for that as well. But little bit about the whole borrowing thing, right? So even though borrowing errors, and this is in fact one of the very common first things that Rust developers that would run into when you're learning Rust is the compiler will be giving you a lot of warnings about allocations that you're doing. Either something has moved or something has been borrowed already, but you're trying to access it later. So this borrow checker will throw you a lot of errors in the beginning because your understanding is obviously limited, but then it may be very frustrating as a result. However, you are ruling out a lot of issues that are related, that are associated with those practices. And you are in case of Rust, we are able to actually eliminate all of those issues at compile time itself. So we don't at runtime have to go and trace memory related issues. Okay, what is happening? Maybe something that I allocated is no longer it has already been freed, or something that I have multiple reference to, multiple threads are writing to it, and things like that. There is a lot of issues that are actually completely eliminated here at compile time itself because of simply following these rules, right? And like I said, so we can have mutable references as well, but then again there are certain additional rules, which is that, okay, so we cannot have mutable reference while we have an immutable as well. So that is also a restrict. So which means to say And this is also something that can lead to a little bit of confusion. But so when you have a reference to some memory that has been allocated, by default, if you remember, when you're borrowing it, it is an immutable reference. Now, by immutable meaning it is a read only, so you can only read. So now, while the Rust SQL, the compiler, it will allow you to create many immutable references to an allocated memory, and that is allowed. However, if you want to create immutable reference, which intent being you want to modify what is there in memory, but then you're only allowed to do that. So you can't have both an immutable, which is to read, and a write. So even those are not allowed. So either you do write, which is you have a mutable reference, or you can have many immutable references, but they are mutually exclusive, right? I mean, premise is very simple, right? So the idea is, okay, so when I have immutable references, we don't expect that the value will suddenly change or somebody is going to write to that. And again, it's a matter of ownership as well. So when you've taken ownership as if in the form of a mutable reference, and it is understood, then nobody at the time can actually even read it. Doesn't make sense. You do your work, and once that is out of scope, um, then you may still have immutable references to that where you're reading it, oppose that, but then at the same time you cannot do it. And this whole thing, basically, the main thing that is this is preventing you from doing is having tangling references, which is that you have a reference to memory that had been allocated, but it has already been freed up, or it has been written to or modified in some way. But then you're still trying to read it, and typically a lot of issues are associated with this. For instance, you may be reading memory that is not been allocated by your program, or you may be reading memory that was never allocated. So there are a lot of issues, that buffer overflow and other kind of things that can happen as a result. We are avoiding all of those here, right? Like, because the compiler itself will guarantee that the references are following the rules, like we discussed, the ownership and the borrowing. They're following the rules that have been put in place by the compiler. So in addition to that, there's also bounds checking. So bounds checking is, so when we have things such as arrays or vectors, right? So bounds checking is what basically prevents buffer overloads and those kind of issues. So when you're declaring, even though they are dynamically allocated and the sizes can grow and shrink at runtime, however, bound checking ensure that you're always only ever reading stuff that has been allocated, and never you never exceed or go outside of the boundaries uh, that has been assigned. So that prevents, the compiler itself will check and prevent you from doing that, because it will do those bound checks. Then the next concept, which also gives you memory safety, basically, is this whole concept of lifetimes. Now, so lifetime is a construct that the compiler it uses to ensure that all the borrows are valid. Specifically, a variable's lifetime begins when it is created and ends when it destroys. So the lifetime is basically the time between which that is valid and can be used. Any time outside, before or after, is basically invalid. That memory is not basically, that is not accessible to the program, right? It's only accessible during the lifetime of that, and that lifetime basically in this thing is a first class system citizen, that we can have explicit lifetime associated with certain memory that has been allocated, and that lifetime may either overlap or be shorter than the calling function, for instance, right? And there are rules that govern that as well, right? So it's basically, in some sense, it's something like scope, right? But they're not exactly the same. It's very similar, but then they're not exactly the same. So there's an example. So for instance, the case when we borrow a variable using an ampersand basically gives you it's like a pointer, but it gives you a reference to that. Now the borrow has a lifetime that is that is determined by where it is declared, right? And as a result, the borrow is valid as long as it ends before the lender is destroyed. Meaning, basically, again, it's even though they are related, which is like, okay, the scope determines when it is destroyed, but then the lifetime is just the concept of, okay, how long or in what duration it is actually valid. Yeah. So then there is like a small example which sort of describes, okay, what does it mean by lifetime? So in this example, for instance, we are it's a very simple program where we instantiate a variable I and assign a value 3 to it. And so one minor point here, so, and I think I will come to that, but so here when we assign this to 3, it even though we have not explicitly defining what type of this variable is, Rust also has type inference, so it knows, okay, what type it will be, and it will basically assign the uh, most applicable type if you do not provide it yourself. So in this case, for instance, when we open a curly braces, essentially this is to say we are sort of creating a scope by this block. And so when we say, let's say borrow 1 and we say ampersand type, we create a reference. So we are borrowing that value, or rather, so we are borrowing that here. And so the lifetime begins as soon as the borrow is done. So here is when the lifetime begins. We can actually use that in some way. In this case, they are basically printing that out to std out. But once that block ends, that's when that borrow is no longer valid, and basically that memory that borrow will no the lifetime would have ended, and so that is no longer available. So for instance, even though we have declared here borrow 1 and we are doing something, once this ends, if we were to try to access it outside of that scope, then the compiler will basically give you an error saying, that is no longer, in there's no longer valid, so you cannot actually access it. And again, this is another basically showing, okay, so even though this is within one main function, again, you can have many sub scopes and stuff like that, and then within those scopes, the whenever you do the borrow, the lifetime is only within that scope. And even though you can have many such blocks and smaller scopes within one linear code path, but those lifetime can live much shorter than the bigger one. The main lives longer, but then these individual blocks, they live for much lesser time. And there are times when, for instance, the lifetime may also exceed the actual function's lifetime. The function may live for a certain time, but then the lifetime of stuff that you declare or you return might exceed, because the lifetime may be dependent on the one that is calling this function. In this case, of course, it's main, but it could be any function. So if some other function is calling and giving it some arguments and stuff like that, then the lifetime of those would be determined based on where it is called. And so in that scenario, the lifetime of that allocation would outlive or would be much longer for anything that is within this function. Yeah, it might be a little confusing, but I think once you work more and more with this thing, it becomes a little bit more apparent and understanding. A lot of the time, we don't have to worry about it. The compiler itself, it has this whole um, uh, basically it will mark each and every scoping thing and everything behind the scene, create lifetimes, and actually keep track of them, so you don't have to do any bookkeeping of any sort. However, there are times when being explicit about, okay, what are the lifetime, you can even give them names and stuff like that. There are times when being explicit also can help the compiler in a way to, especially when the behavior is not as apparent or obvious. But then this lifetime concept, along with the whole concept of borrowing and ownership, along with that, it works in tandem. And also, again, basically, it's a way, or it's a mechanism that allows us memory safety, right? Okay. So the next thing, again, from the key things that are there in Rust is this whole concept of zero cost abstractions. So what are zero cost abstractions? The idea of zero cost abstractions is that basically you are writing high level code that may look or behave in a different way. However, behind the scenes, when it is actually compiled and it is in the most optimal form as can be. For example, if you compare and contrast that to something that you've written in a very low level programming language such as C, maybe you, or even assembly for that matter, as a matter of just comparison, right? The idea is, even though you might be writing code that is complex and from a syntax standpoint, behind the scenes, it is still as optimized as possible. And so that's why they say there is a zero cost. And so this however is not true for all programming languages. So a lot of programming languages may give you a lot of syntactic, sugar and stuff to do a lot of things. However, behind the scenes, there may be a lot of runtime cost to it, uh, which is that, to actually achieve that, or to translate that at runtime, they may have to spend some additional time for either translations or bookkeeping or things like that. But in Rust, you know the compiler is giving you these abstractions which look nice and neat, but then there is no runtime cost of it, right? So it means that, so essentially that means that Rust allows you to write code at a high level of action without sacrificing performance. So this is the key here, right? Because there is no runtime cost to these, there is no impact on performance as well. So you're still writing a code that is as optimal as possible. So here we look at an example, basically, right? For example, we're declaring a vector which is, so in some sense, basically like an array of numbers here. And what we do is, okay, so we say, okay, sum of squares, which will be of type int32, is, we say, okay, numbers iter, and what iter does is basically it gives you an iterable, and in an iterable you can actually call map on it, which is like a functional map, which is to say, you're actually going through this thing and then transforming it and returning something else. And so in this case, what it does is it gets a reference to the actual number contained within the iterator, and then we say, okay, basically we are saying we are squaring that number. X star x means multiply that by itself, so we are squaring that number. And then also at the end we are calling sum on it, which means, so now what we are saying, we square each of the numbers and then we want to add all of them, and that will be my final value, right? So if you think of it in a functional way, you might think what this might do is that I create an iterator, I will loop through it, and then create a list of values that have been squared. And then finally, again, I will iterate through them and do a summation, right? So typically, you might think of that. And in some programming language, that actually would happen. And so that means that it's no longer happening in one single iteration, right? However, here in Rust, even though you might express it in this fashion, and for instance you could apply multiple subsequent maps as an example, right? You could apply multiple maps, do different kind of transformation and stuff, but at the end of the day, when this is translated, by the compiler to machine code, it would be a single iteration in the maximum optimized way. And so that's the reason why there is no runtime cost, right? I think this is a pretty straightforward example, but it shows you the power. So even though we are expressing this operation in this sort of functional chain of operations that we are performing, but then at the end of the day, it's all done in a single operations in the most optimal fashion. Then, of course, yeah, comes the whole point of concurrency. And so let's talk a little bit about what concurrency is, and then we'll talk about how Rust approaches it. Now, handling concurrent systems, concurrent programming safely and efficiently is, one of the Rust's major goal as well. And so concurrent programming is basically where different parts of a program, they execute independently, and parallel programming is where different part of a program execute at the same time. So this is just to sort of contrast between, okay, what concurrent programming is and what parallel programming is, right? So parallel is when they are executing at the same time, where concurrent is where different parts are executing independently, which is to say they're not interacting. But then whether they are doing parallelly or not, it's subject to different parameters. And basically your runtime will determine exactly how that execution metrics are going to be. Now, historically, programming in these contexts, when you write concurrent programs, there are error codes. There are various issues that are unique to concurrent. When you write concurrent programs, things like deadlocks or accessing when you have shared access to memory and things like. So there are a lot of these issues that are unique to when you write concurrent programs. However, because of the whole ownership and stiff system that the Rust comes with, the whole borrowing ownership and mutability in the reference and lifetimes, all of these rules give Rust sort of this unique advantage where none of those issues are uh, uh, are you know are inherent in Rust system, because at compile time, even though we are writing, we have the ability to write concurrent programs, but then because we are still ensuring all these rules are applicable, it also translates very well to concurrent programs and still gives us that memory safety, and then so our programs will not run into those issues. So it's sort of like a history minor thing is, the Rust team, when they initially were designing it, so they thought that ensuring memory safety and preventing concurrency problems were two separate challenges that we should address. However, over time, that they discovered that this ownership and type systems that they are creating, they are basically a powerful set of tools that, to help manage memory safety and concrete problems both at the same time. So this whole concept of ownership that we looked at, right? So even though initially it was assumed that we still would have to solve them independently, it just ended up, we realized that this one thing solves both problems. So by leveraging the ownership and type checking, memory concurrency errors are compile time errors in Rust rather than runtime errors. And this is very, very important, right? Compile time errors is, you're catching the error even before there is one. Whereas runtime error, meaning, it will basically involve a lot of debugging and understanding what is happening and how memory is allocated, who is accessing what part of the memory, what mutations are happening. So if there are errors at runtime, it's much harder to actually detect them, debug them, and fix them. Whereas when you're catching those issues at compile time, it gives us a huge benefit, right? Yeah. So a little bit about, okay, so how Rust gives us this basically is, okay, so you have threads, um, and this is very similar to a lot of others. Basically, you can create threads that are basically sort of these self-contained stuff which would maybe doing some computation, right? And they can be done concurrently. And but in Rust, typically these are green threads, which are not OS level threads. So again, depending on, and one of the key things about Rust is that, even though Rust has very good support for concurrency and, parallelism, however, it is not part of the language itself. Basically, the language gives you a few things which we look at a little later, but gives you a few basic concepts which anybody can come in and implement, and then that basically forms the basis for a runtime where you can have these ideas implemented. And as long as we are obviously adhering to the rules that the programming language lays down, we are, guaranteed that they will be, or at least we are reasonably guaranteed there wouldn't be issues that are related to those things like race conditions, deadlocks, and memory allocation, memory reading, and when shared access happens and all that. All of these would be avoided as a result, right? So we have the whole concept of threads. We also have concept of message passing. Message passing is basically, when threads can communicate between each other by sending messages. And this basically idea, I think, is more popular, for instance, in something like Golang. And this slogan that the Go language documentation gives you is, do not communicate by sharing memory, instead share memory by communicating. And it's a good thing. But then, so yeah, so message passing is basically that. And to accomplish message sending concurrency, Rust standard library basically provides you an implementation of channels. Channels are basically a general concept, which is very similar to Go channels, for example, right? So it's a concept that allows you that you would transmit a data, and then there would be a receiver that will actually receive that data. And so the transmitter would be in one thread and the receiver can be in another thread, right? So channel has these two halves. There's a transmitter, there's a receiver. The transmitter half is the upstream location where you put rubber ducks into the river, and the receiver is the half where the rubber ducks ends up downstream where you receive that, right? I think, yeah, I think that probably uh, is enough about that. And then you also have shared state concurrency. So shared state concurrency is when you're actually sharing memory between threads. But then, of course, there have to be certain things that has to be followed in order to make sure that there is memory safety, right? So while message passing is a fine way, but it's not the only one. So in Rust, you can do either message passing through channels, or you can also you have tools for doing shared memory access as well. And even though this goes against sort of this goals philosophy, right? They do not communicate by sharing memory, but it is still an option that you have. So basically, the few things, as an example, what Rust provides is, for example, mutex, right, which is an abbreviation for mutual exclusion. So it allows you only that, okay, it will allow only one thread at a time to get access to it. It would have to, and anybody who wishes to basically mutate that particular memory, they would have to acquire a lock. And the idea is basically that acts as a synchronization between threads, because when somebody acquires a lock, then all the other threads that wish to read that reference would have to be blocked, would have to wait until the lock has been released. And this is a common design pattern. It's just that Rust also offers you it. And there are a few other things that are there within the Rust programming language. Like there's also ARC, which is an atomic reference counter, which also again provides you an ability to do the similar stuff, where you can basically have clones of it, and then multiple threads can read through it, but it's thread safe, which means that there will not be race conditions or issues. And then, so yeah, so this is what I was talking about initially. So basically, the language does not provide you the runtime for concurrency. It only provides you with this extensible concurrency with these ideas, and so which is tied to these two things. There is a sync trait and there is a send trait. And this is also kind of very interesting, because the language itself, it does not give you much. It only gives you these very few features. However, it's up to the implementer who would implement these traits to be able to design how the exact behavior is going to be, but as long as they are following the rules, right? And so typically the idea of send is basically, it allows transference of ownership between threads with send. So anybody that will implement the send for any data type, and by the way, by default, most fundamental data types we have in Rust are both, they do have sync and send for them. But however, of course, if you're creating custom data types and stuff, in that case, if you're implementing your own asynchronous runtime, then it would be your job to actually provide the implementations for these. And so, like I said, so the send is basically that defines exactly how the transference of ownership will happen between threads, and then sync is basically, okay, how you allow access from multiple threads. So sync basically controls how the access happens, whereas send is basically how we are transferring the ownership. I think there's a question. Yeah.
Dhruva, sorry, just a quick update. 10 more minutes.
Yes. Cool. Yeah. I think it will go pretty fast now. So that was basically, a bit theoretical, and then on a high level, what are the things that Rust provides that make it unique, and that sort of give the programmer, the developer, the advantage that, you're writing code in a very high level language. However, you still are not doing as much as you might do, for instance, in something like C++, especially when it comes to memory. And because memory safety issues are, the sort of the most important issues that are in any program, that's why even though you're writing low level code, and you still don't have to worry about it without paying the price by having a garbage collector. That's which makes it sort of unique. So yeah, so you could install Rust. I think you could follow Rust Lang's guide. You could install Rust. You'd also have to get familiar with Cargo. Cargo is sort of the package manager or build tool. It's like all encompassed. Like it is a build tool is the package manager for Rust. And then in addition to that, you also have a very cool project called Rust Analyzer, which is a modular compiler frontend for the Rust language. It's basically like a language server, but then it does few more things beyond that as well. But then it is within that whole RLS, which is the Rust language server protocol. for very good IDE support. Basically, this is what allows any IDE to be able to deal with the Rust nicely. Yeah. So we'll go over the basic syntax. For instance, I think we've already seen a bit. Like for instance, you can declare variables in this way. So in this case, we are not explicit about what the type is. So the compiler will go ahead and infer the type which is most applicable. In this case, we are being explicit what the type of that variable is. In this case, we are declaring, okay, by saying mute, we are declaring that the intent is that we want to mutate this variable. So another minor nice thing, right? So when, for instance, if you declare a variable as mutable, however, in the code path, you never actually mutated, the compiler again will give you a warning and an error that you're not actually mutating it. Perhaps you should remove the mute. So these nice things are obviously also there. However, if you want to actually change it, the other reverse is also possible. So if you declare an immutable and you actually try to change it, the compiler will again say it's not declared as mutable. So we'll go over a few data types that we have. There are obviously the scalar types. We have integers, floating point, Boolean characters. And then there are compound types. We have concept of tuple, which basically arbitrary number of stuff combined. We have arrays. In arrays, we have this whole idea of slices and vectors. Slices basically typically are fixed length, whereas vectors, are dynamically allocated that can grow and all in size and all that. And we have functions. Functions basically by the keyword fn, you can declare a function, and the function would have an argument list, and it can obviously have a return type as well. So in this case, we have small function, a main function, which is doing a hello world print, and then it's calling the other function. The another function is just printing out another. So if you were to run this program saying cargo run, you would see this, okay, it compiles and then it will get a dev. By default, it will be a dev build, which is, it'll have a bunch of debug info and all those things. And it would generate a binary, you will run it, and then obviously you will see in this sequence, it will first print out hello world, and then the another function will print its output. And then the other thing you have are structs. So this is also one of the more fundamental stuff. Coming from C++, people would typically be very familiar with this. But yeah, so the idea of is basically a struct is like an encapsulation of different, basically you can create custom types which would encapsulate different properties that may be. So in this, for example, we have a rectangle which might have a width and a height. We declare it in this fashion, and we say, okay, it has a width of type unsigned 32 integer and then a height of an unsigned 32, and then you can provide an implementation for that in which you can define functions. And in this case, we say, okay, it's a function on an and self, which means it's a function on, it's like an instance method for the rectangle. So any rectangle, so we'll see that here. So we create the instance of a rectangle, rect1, and then we can actually print out by calling rect1 dot area. And because it's an it's a function that is bound to the instance, to the reference of that, and in that we do return this calculation. So this is how you declare, okay, this return type is unsigned 32, and in this case we simply return product of width and height. So this is basically a small example of structs. Yeah. So then Rust also has enums and pattern matching. I think this is also pretty cool. So enums are pretty straightforward. I mean, if you come from other types of the languages, you would be familiar with them, the concept. Basically, it's like a bunch of properties within this thing. So for instance, coin could be either a penny, nickel, dime, or a quarter. And then what you can do with the help of this construct called match. So for instance, if you had in this function, what it says, okay, value in cents, and it receives an argument coin of type coin. So the type of this is the enum coin, but then the actual value could be either of these, right? It could either be a penny, nickel, dime, or a quarter. And so here, when we say match, we can actually provide all of those matches as the thing, as possibilities. And so for each of those, we can have a branch of code execution path. So in this case, okay, if it's a penny, we return 1, nickel 5, dime 10, and quarter 25. So With the help of this match, we can do pattern matching. So we can match against, okay, what the type of that will be. And this is also very powerful. Okay. Yeah. So ecosystem and community. Yeah. So I think the Rust standard library is actually very rich. And it has a lot of collection of pre-built modules for most use cases. You have package management, which is built into the build tool that ships with Rust, which is Cargo, right? Which means you don't have to download or learn something like have something additional. And it simplifies dependency management. And then it has a very, it's a growing community with a lot of open source projects, resources. Yeah, I think so. There is obviously rustlang.org, which is sort of this official Rust website, which itself has a playground and a lot of guides and tutorials to actually learn the language. There is also a very handy called the sort of this Rust programming language book. uh, I think it's actually a very good resource to learn the language in a much more detailed fashion, because it has all of these chapters which cover a lot of the topics which we looked at as well, but then it covers them in a good amount of detail, as contrast to the Rust's official website. Here it would be more about, okay, getting used to and understanding. This is a bit more, this would be, I would say, the next step. Once you are familiar with the basics, then you could dive deep into each of those concepts here, in a good way. And then, of course, yeah, it's because there is a ton of open source projects that are there. I would definitely encourage you check them out and even contribute if you can. Yeah, it basically covers everything, I think. Yes, go ahead. Um,
Cool. So
yes.
I just wanted to say there's also Rustlinks, which is amazing.
Oh, yes.
You should
I
get
saw
started with
that.
it. Yeah. Yeah.
Yes.
Rustlinks is it's like sort of like a GitHub course where you can just do some katas, make sure like you fix failing builds and all that. And this is similar to like what Ruby Covens or even this Ziglinks is. So which came from Rustlinks. So I kind of learned Rust from Rustlinks first, and then I went through the book. So I was going between the book and Rustlinks, and it's actually pretty good. Yeah.
Yeah. Yes, I missed that. Yeah, actually, I discovered this only after I started with Zig, interestingly. But yes, this I think is also a very good resource.
Yeah.
The idea is actually very novel. So the idea is basically it has a series of it has a long list of code that has already been written. However, your job is basically you compile and you will be presented with compiler errors, and step by step you will solve compile errors. And in the process of that, you'll basically become more familiar with the syntax and the compiler and the kind of issues that you would encounter, and gradually incrementally learn and get better. Yeah. Any other questions and stuff? I think I know this was a bit uh, dense, but I think once you play around with it more and understand some of these concepts, I think memory safety is one of the most special things for me as well. The way Rust approached it. One, of course, it is very novel for developers, makes things easy. However, like from a language design perspective, it's actually very, very interesting to actually understand the ideas behind it, and how the different approach that they took made so much of a big difference when it comes to developer productivity and being able to be safe.
Okay, so that's awesome. Thanks, Dhruva, for the introduction of Rustlang that walking through. Any questions? Anything? Please, we can take a couple of minutes and talk now. If not, we can start the workshop by Vagmi immediately, or we can have a small 2 minutes break and start it. But I think Vagmi, do the folks need to do anything to get started? Is it something which we install? Maybe you can give the instructions.
Yeah. So yeah, sure. So I've also just started streaming on my LinkedIn and things like that as well. So yeah. So for some karma points here. So anyway, so I'll do that. So just a quick round of introduction. I think most of you already know me. I'm going to share my screen a little bit. And okay. So I'm Vagmi. So I basically, I mean, and coming here to Chennai Geeks is like really nice for me because this was the first message that went to the Chennai Geeks community by Dorai, and this was our first, I think, meet. I think this was, I think it happened the day off or the before the day. I don't remember, but Dorai basically sent this mail out because I think the first meetup for Chennai Geeks happened at the ThoughtWorks office in Chennai at RR Towers. They were not even at Tidal Park. Oh no, what was it? Asendas at that point, right? So it was there. So it was a really sort of like a cool thing that we did started off, and I'm happy that it's been going on, even though it's been long since I was running it. So thanks to all the group here, and the community is amazing actually. So I'm going to talk about Axum, but I'm going to let you guys take a little bit of a break before we come back. Regarding what you need to set up, not much actually. So if you can go, if you already have Rust on your machine, that's fine. Otherwise, just go to Gitpod, and then we can go from there. Gitpod is like an online coding environment, and you can follow me through. So I built this workshop for that conference, and it was a 4-hour workshop. So I'm trying to condense it down to 2 hours. So some of the fidelity may be lost, but we can keep it interactive, and we can go from there. And any questions, please feel free to interrupt me. No need to raise your hands because I can't see the screen. So yeah, just go ahead, go for it. Cool. So you guys want to take a quick 2-minute break before we get started, or should we get started?
I'll wait for others to say, someone to say. Okay, I think maybe Wagner will start right away.
All right, perfect. So I'm going to also put in.
Someone asked for to need 2 minutes to set up. Maybe we'll wait for a couple of minutes. And then,
okay, cool.
Yeah.
All right.
So while we are waiting, Vagmi, by end of this workshop, we'll be building a web application. You're on mute.
At least have a Axum sort of like a service up and be able to receive requests. So the idea is that, okay, we'll walk through just the just a simple bit of like, okay, set up an endpoint, receive a request, and when you receive a request, will look like, okay, do you want to get the information through path parameter or a JSON request body? How do you respond to JSON? Also, how do you connect to a database and then like do some basic management over there and all that? So it's like a simple CRUD app. It's like a to-dos kind of like an app that we are trying to build. Yeah, and let's see how far we get with that.
Awesome. And there's a question from Shiva Chandran.
Yes,
do we need to create GitHub repo to use with Gitpod, or we can just directly maybe?
Yes, we would. So what I will do is I wanted to do it as a part of that. So we can actually.
Then we can start it so that now you can show us how to start things in Gitpod.
Yeah.
Follow.
Yeah. Let me call this and.
Yeah, it's very small. The font size.
Okay. Yes. Is it better?
Yeah.
Okay. So let me go and get in it. This. It's like a very bare bone repository. I need to add. Let me create a remote. Right. All right, so this is there. So let me show you how Gitpod works. Is everyone back? Should we get started or should we wait for a few more minutes?
I think we can start.
Okay, cool. So yeah, before we jump into the action, I just want to quickly sort of like talk a little bit about Axum and give like a background context so it's kind of framed. Axum is a web framework under Tokio. I think Dhruva talked a little bit about Tokio and async and concurrency and all that. We'll be getting into it a lot more. Again, I think this screenshot was taken out roughly a year back, so the commits may not align or things like that, but it doesn't matter. So who am I? I mean, so I'm Vagmi. As you know, I've been writing code since 2001. I work at Taka Labs now as the CTO. So I mostly write, I mean, I like writing code in Rust, but I also deal with all kinds of other programming languages, things that you cannot get away with, like TypeScript, JavaScript, and things like that as well. And I've also been doing a little bit of Python and machine learning and things like that as well. So my interests are a little bit varied. I'm a bit of a scatterbrain in that regard. So why do I like Rust? I think Dhruva covered a lot of this, but these are some of the few things that I like the most, actually. So I like the types and trait system in Rust because I've done a lot of dynamic programming languages as well, like Ruby and things like that. I still love Ruby, but I don't love its performance, but I love the expressiveness of Ruby. And I also have done Haskell. I like Haskell because of the way it thinks about types and functional programming and the purity. And the where I fall off with Haskell is when people start talking about category theory stuff. I can follow some of it, but then I somehow feel that it's needlessly complicated. And Rust kind of hits the sweet spot. It has enough type theory for us to understand, but at the same time, it's not too academic where you don't have to go and read a paper about what lenses are, or things like, okay, monad is just a monoid in the group of this thing, whatever, right? Endofunctor and things like that. So you don't have to worry about all this stuff. So it's very practical. It can get the job done. It has a really nice syntactic sugar, just like how Ruby has, in terms of like, how do you do error handling, right? You don't just throw exceptions all around. Like, you don't have these kind of like unpredictable code paths as much as possible. You could have a result type where you can basically have a success or a failure. We'll talk about that and we'll show. And Dhruva talked a lot about the borrow checker, so which is a very interesting way of doing this. And I mean, we have all dealt with memory safe languages. I mean, like most of the languages that we deal with day to day are memory safe, so it's not that big a deal. Where it becomes big of a deal is when you want to target, non-standard environment. So if you're not directly deploying it on a CPU, and then you want to build a VASM, or you want to build it on, say, a Pico or some ARM hardware or things like that. So that is where I feel the strength of the borrow checker is, right? Because it gives you that kind of a guarantee with a high-level expressive language without you having to muck around with, pointers and, dealing with memory management yourself. And it heavily has inspiration from functional programming languages. I think Rust's initial version of the compiler was built with ML, and also it has macros, right? So and macros, they have the standard sort of like the hygienic kind that you find in Scheme, as well as proc macros, which are like, you can do pretty much anything you want with it. I mean, you can build your own sort of like a mini language with macros, which is amazing. I mean, we have seen all kinds of things built, like including full JSX support in Rust called RSX. So which is cool. So macros are amazing. Async await, Dhruva talked about it a little bit. It's about concurrency, and we'll talk about it as well quite a bit. So I'm going to leave it there. WASM support, this is amazing as well. So WebAssembly is not just for the browser, but also it's like a very nice sandbox target that you can have when you want to run untrusted code. So if you want to enable plugins on your website and things like that, the standard way of like running untrusted code is basically through a Docker container. Throw it in a Docker container, and then like if something bombs in there, it's basically, I mean, you reduce the blast radius. With WASM, you can actually make it much smaller, and you can just give the kind of interfaces you want with it. And again, this is not something new. Game engines have been doing this for a while with Lua. I mean, Roblox does it, where it allows you to arbitrarily run code. But the cool part is now you can have like a low-level language with a high performance and have the ability to do it. And then there is the zero-cost abstractions, which is again a really cool thing. It's from C++ kind of ways that you're doing this, where you have all these compile time constructs that you want to do, but then when you compile it down, all that goes away. So like in Ruby, if you want to do dot map or a dot the reduce kind of like an operation, and then or you are doing a tight for loop, they have very different performance profiles actually, right? Because you're creating stack and you're unwinding stack and all that. But since Rust knows all about it at the compiler level, so when you do a dot map or a dot filter and you want to have that sort of like expressiveness, it's exactly the same performance profile as if you had like handwritten those loops. So it's amazing. So that's it. I don't want to like keep us away from the code, so we want to get to it. So I have created a Git repo here. I'm going to share that on the Meet chat. Yeah. So, and then let's go to Gitpod. You can go to dashboard. I'm going to create a new workspace, and I'm going to put in github.com/Vagmi/CG Axum workshop. You can feel free to fork it, or you want to do this. GitHub hasn't caught up. I'm sorry, Gitpod hasn't caught up, I guess. Oh yeah, it does. I think you need to paste in the full URL, and you can basically have VS Code, whatever standard stuff is fine, and you should be good to go. So we'll start off with this. I'm going to switch back to Vim because it's this, but let me get to this. So this will basically give you the first sort of like a version. So let's run this. It's already running. It's having a cargo watch -x run. It added this Gitpod YAML as well as a part of this. I think I need to pull that down. So which basically tries to run this. And if you notice here, it starts with the cargo package that we have here. And it has a bunch of dependencies. Right now, we don't have any dependencies on the project. And then we have a main file here. So let's start from this. So just, I mean, whoever wants to follow along, if you can give me a shout out You can unmute your mics and shout out, or if you want to do this, or if you have any, if you need any help, if you can throw on chat, I think we can. I mean, Sudhakar can kind of like interrupt and then let me know, and then we can go from there. So I'll give you like 30 seconds or so. Make sure this is up and working for you. All good, everyone? Are we good to go? So I can't see the screens, but I'm assuming we are all good to go. Okay. All right, so let's run this. And we should see hello world. Very underwhelming. You don't need to know Rust to print hello world to the screen. But let's make it a little more interesting, right? So, so how do you add a function in this thing? So we'll add a greet function. Again, I have Copilot. Maybe we'll disable Copilot, but we'll keep it. It's fine. And then we'll call. So right away, we are faced with this weird ampersand here, right? So this ampersand, I mean, if you have C-based things, it kind of is like oh, this is an address to a pointer. So it's not quite an address to a pointer; it's more kind of like a reference. So here you don't get access to actual memory in Rust. So Rust kind of like guards you from that. So all you get is simple like, hey, this is an object, but this is a reference to the object, and you let the borrow checker kind of deal with it. Right, so you cannot do any pointer arithmetic map like, oh, you get an address to a string. Can I do a +1 on this and things like that? No, Rust does not allow you to do this for very good reasons. So let's run this. Argo run, and it says hello Chennai Geeks, so which is cool too. So let's add a little bit of a structure to our program. So what we want to do is we want to create a module called greeting and then place it in that. So let's do this greeting, and we'll put this in the module, and we'll call this greeting greet. And so when you
some functions as exclamation mark like println, do they mean anything?
Yes, I will get to that in just a second. So println is really not a function, but a macro. So let's see. So what we did is now we created a module, and we basically are going to expose this greet function from the module, and we're going to call this here. So here, the way I call this is like, say, greeting greet. So even with this, now we should see our greeting kind of come up. So this is cool. So at some point in time, you need to start organizing your program into different like files, right? So, and modules are a natural way to organize code in Rust. So you have two ways of doing this. So I can do greeting.rs here, and I can move this bit into greeting.rs. Okay, so maybe I should create a commit before I do this. So let me do this, and let me create a commit on this for this, so that for others following along, I think it'll be good. So greeting unchecked. So we just added mod greeting, and we've done. Okay, this is good. And what did we okay, we changed cargo.log. Yeah, the first time it runs, it creates cargo log. That's fine too. So we'll commit this into this. All right, so let me also push this up. So in case others are following along, you can start from this point. So now we come here. So what we'll do is we'll move this greeting to its own sort of like a file. So I created a file here called greeting.rs, and I'm going to move this here to pub function greet. Okay, and I'm going to go to this thing, and I'm going to basically say, hey, this is in an external file. So we just declare the module here. So when you declare the module, and then we have this, so this would be right. So this is the same as the previous one. So what we essentially did was we moved greeting to its own file, and we did a pub function greeting. So if you can see, this is very similar to how you do like with JavaScript or something like that, where you create a module and then you import it and so on and so forth, right? So we are directly saying greeting here, but we just want to say greet. So how do you do that? So there you do a use, and you say greeting : greet. Oops, sorry, I fat fingered it. And you can have greet here. So this would be the same thing. So you can do a cargo run, and it says hello Chinese. So this way now we have figured out how do you create a module, how do you create a function within a module, and we do this. Now we want to make one small change to this, where instead of printing it, we want it to return the file. So right, it will take this and it will basically do a.
Hey, Vagmi, should you give us a minute so that we'll catch up with you?
Yes, please. Yes, please. Yes, please. Yes, please.
So I think as long as they're able to get a separate module, greeting.rs, and then call that from main.rs and execute it without error, we are good, right?
That's right. That's right. So let me just quickly find out, is there anything else in chat? Okay, no, good.
I'm looking at that, don't worry.
Okay, cool.
Hey, others who are trying it out, running it, feel free to just stop Vagmi. He'll be very nice and he'll definitely help us.
Yes, definitely. I mean, the goal of this is for me to convert you all into Rust fans, so that you can go back to wherever you're working and say you want to rewrite that project that you're working on, whatever it's in TypeScript or Go in Rust. Rewrite it in Rust.
Okay, I got it.
Cool.
Others, should we proceed or wait for some more time?
Yeah. So what I'm also going to do is I'm going to basically make sure that I println the value that I get out of this. So what I'm trying to do here is it says one unused. It must be a string literal. Oh yeah. So just want to make sure. Come on. Right. So what I did here was basically turn this into a string, that it returns a string, and format basically allows me to do kind of like string interpolation into this, and then it gives me a string back. So format basically returns a string. So it converts the single value of string to string to this method. Okay, so that's that. So and if you notice here, I don't have a semicolon in the end at this line, right? So if I don't, so this is the same as saying return format semicolon. So it's the same. So just like how you have in Ruby, so if the last evaluated expression is returned, so you don't have to put in return here, and just put you just avoid the semicolon at the end. So it becomes from a statement, it becomes an expression, and that gets evaluated and returned. Okay. With me so far? All good?
Yeah.
So you should still see Chennai Geeks, and then because we are println this out. So now, so it wouldn't be my talk if I don't have tests in it. So more tests. Let me add this. So Copilot is just so great. I mean, I love Copilot. So so here as a part of the test, so I want what you say. So just like how we did mod greeting before, so here in the greeting.rs, we are doing mod tests here. Okay. And we are basically telling the compiler saying that, hey, you know what, when you create this binary out, make sure you don't include it, right? Because this is used only for tests, right? This is not used for other things. So the compiler knows not to include it as a part of our either the debug or the release binary. In fact, it's going to create a, and even for tests, it's going to compile its own binary and basically going to run these tests. Okay. And here, so what are the test functions you want to run? So it basically allows this. So you can say cargo test greet, that's there. And then it basically says greet. When you call greet Chennai Geeks, it expects it to be hello Chennai Geeks, right? So this is cool. So let's run this, and let's run the test. So so here I'm going to start pulling up a terminal side by side, just so it's there. So cargo test, and then it'll run the test for us. Okay. So we can create another test just so I wanted to show how you can run a single test. Okay, so I have two tests now, a test greet and test greet 2. So if you just want to run this test, right? So you can see it's actually running greeting test. So you can say cargo test exact, and you can give test greet. Okay, I think cargo test. Okay, so this is only going to run that one test. So it's not going to run test greet 2. So if you want to run test greet 2, you just run this test. Right now, where is this useful? IDE integrations, this becomes really cool, where you can run this exact test that we want to do that. And there is something interesting happening here. So when you're running cargo test, so this is basically going to execute the test binary. And then for the test binary, it's going to pass in these parameters to the test binary. Does it make sense?
Vagmi, if someone is using Gitpod, I think Shiva Chandran is asking, it is running the main automatically in the Gitpod. Is it possible to use Gitpod and run all these tests and follow this?
Oh yeah, sure. So let me pull this up to Gitpod. Just give me 1 second. So so let me add this Git. Let me push this up. So if I go to my Gitpod instance and refresh this, okay, let me go back to the terminal. In fact, let me trash this terminal and start another terminal. So Command J is to start the terminal. So and then you can say git pull, and then you can say
Vagmi, about it, yeah. Okay.
yeah. Right. So right. So the same thing would run, because now you are in a terminal that's there. So in fact, with here, you should be able to run this test just like this, or here. So with Gitpod, it makes it actually even easier to do this, but this is exactly what it's doing. So if you see here, this is what it's doing. So it's actually going to run greetings this thing, and it's going to run exact, and it's going to run that binary for that package. So it does this. So if you want to actually do this, you can actually even do the same thing here. You can come here and you can say cargo test exact. And then you can run that test basically. So you could say greeting. So what did we run?
Yeah, I think.
Yeah, greeting testing.
Shivchandran, are you able to get to here? Okay.
Right. So yeah, it should be the same. Right. So cool. So that's that. So let me go back to him. This just feels like home, you know. So it's good. But anyway, so that should work too. So we have this. Now, you were asking me about all the bang methods, right? So why is format having a bang? Why is println having a bang and all this? Because these are not functions. So one of the things that Rust does not support is variadic arguments. So you cannot have a function that has this. So because since you have this, you could say println this, and I can actually also do stuff like this. So I can have, I can do something like this, and this won't be a valid function call, right? So there's no way to write a function and overload it such that it can have variadic arguments. So you need to have different functions for it actually. So that is why in Rust this is implemented as a macro. Okay, so let's look at what this looks like. So I'm going to do the format macro. So what I did was I basically expanded the macro here. And when you expand the macro, this is what format actually does. So format basically expands it to create format, built-in format args, and then does this, and then it gets this. So this actually knows how to format these multiple arguments, and then it returns this. So it's the same with this. So let's do this. So this does a create IO print format args and this thing. So these is a built-in. So since they are built-ins, so they can be unsafe code. It can do whatever it needs to do. So, but this is something that is implemented by the compiler. But we look at how cool this macro expansion is. So right now we just have to treat it as a little bit of a black box for println and format. But for the other macros, it's going to become much cleaner, and we're going to see a lot more macros. In fact, you'll be using macros all the time in Rust. You may not have to write your own macros, but you'll be using a ton of macros. So similarly, so we did this hash test, right? So again, this is not a macro here, but this is basically an inbuilt sort of like a Rust compiler feature. But we'll also be looking at how to write macros for like async code and things like that to do this. But yeah, I just don't want to get ahead of it right away. So with me so far, so everyone here? Give me a shout out if you can go ahead and continue. So the next thing we want to do is add.
Yeah, we're seeing a lot of thumbs up.
Okay, cool. Cool. All right. So next thing we're going to do is add Tokio. Now Tokio is I had this thing ready, but anyway, Tokio RS. Now Tokio is an asynchronous runtime. So what does it mean? So as Dhruva said, we have async await support in Rust, but Rust itself does not ship with a async runtime. So while it knows what an async function means, it does not know how to run it actually, and that is where Tokio comes in. Apart from Tokio, there's also async STD, and async STD is the standard way of Rust doing it, but I prefer Tokio because Tokio has been there for a long time. There's also small in Rust, which is a small, fast async runtime. In fact, for if you're using WebAssembly, or if you're doing stuff like on Raspberry Pi Pico or things like that, then you can have a small, because it has multiple processors. You can do some concurrency and wait on I/O and things like that as a part of this. So a small is pretty good, or even WebAssembly would support small. But here we are going to use Tokio. So Tokio is the most mature and the most widely supported sort of like a async runtime. So what does an async runtime give? It gives you green threads. So if you have say 20 tasks to perform, and many of the tasks are IO bound. Say imagine you're receiving a request from a server, and then you're then talking to a database, right? So by the time you receive the request from the server, the only processing your web server does is basically parsing out those HTTP headers or your request body, parsing it to JSON, and then doing all this, and then it's going to construct a SQL query, which is again on the CPU side, and then it's going to send it off to the database. When it sends it off to the database, so database would probably take 20 milliseconds, 30 milliseconds to respond, or 3 milliseconds to respond. But Rust can serve other requests in those 3 milliseconds. So what it does is basically it does the sort of like an evented IO, and that's why it needs to have a pool of workers where it can pause tasks and say, hey, call me back when your IO is ready for me to consume, and then it can call it back, and so on and so forth. So that way it kind of like switches. So and Rust can do pretty crazy amount of like volume and scale and things like that. It's very efficient. It's extremely efficient. So we're going to look at Rust, Tokio, and see where it goes. So there are two libraries here, tracing and bytes, which are outside the Tokio ecosystem, right? So bytes basically figures out, okay, how do you handle byte buffers? How do you read efficiently and then write efficiently to byte utilities and things like that? So, or how do you slice from bytes and all that? So this is like, providing byte stream manipulation, byte array manipulation. It's technically outside the Tokio ecosystem because you can use bytes even outside Tokio. And then there is tracing. Again, this is outside this thing. So Rust has a very, very unique perspective of what logging is. So they don't call it logging, they call it tracing. And you can turn on or turn off tracing at really, really granular levels. Like for example, if you're running a low workload on EC2 or ECS for a container, and you want to only observe one particular crate's output at this thing, you can control those using environment variables, where you say, oh, I want to debug, but I only want to debug this particular crate's this particular pattern, and then it'll do this. And all that can be turned on or turned off with tracing. And it's, like if you're like debugging systems at scale, I think tracing is like a godsend, right? The ideas behind tracing can be implemented in any language. It doesn't matter, but I think there are really good ideas out there. And then there's MIO. So MIO is essentially the nuts and bolts of everything, right? So this is basically like the libuv sort of abstraction that Node.js is built on. So you can essentially use EPOL or KQ or like whatever Windows supports or things like that, right? All that stuff will be implemented at the MIO layer, okay? And then comes the runtime, okay? I don't know why this is there. So runtime is the one which actually implements the thread pool. It implements scheduling. It implements like file system access, because file system is even though it is you're blocking the thread, so you can actually have a separate IO thread for file system and kind of simulate evented IO, even though file system doesn't do evented IO. So you can do this. And then there is Tower, which is so Tower is basically like the connect in Node.js or a rack in Ruby or things like that, where it basically talks about how do you build a server, and then you have limited sort of like capabilities that you can build on top. Like, for example, this is how you do middleware. This is how you do, load balancing, or this is how you do retries, things like that. So all the higher level features around writing servers or writing clients is basically implemented here. And then you have Hyper, which is the HTTP 1.2, and I think they are also supporting HTTP 3 and Quick soon as a part of Hyper. And then you have Tonic, which is for gRPC actually. So they both use Tower, and then you can use either Hyper or Tonic behind the scenes. So that is essentially the kind of the aspect. Now, Axum, the library that we are going to use, is actually not technically a part of the stack. The reason is, even though it is under the Tokio organization, it started off as a separate project by Sean Peterson, and then it kind of like got adopted by the community into Axum, right, and into Tokio and things like that. And we had been using different before Axum came out. I think Dhruva, you can correct me if I'm wrong. I think we used Routerify. I think we have also been using Axum Web. Now, I think even for a project right now, we are doing Axum Web. So there are a lot of different libraries that are available, but this is just my personal preference and my personal favorite, because Axum, I feel, has like, and to a certain extent, I think many features are, many frameworks are copying from each other and so on and so forth. It's just that I started learning Axum and I really like it, and I kind of like stick with this. But again, you feel free to try. But if you are trying something for the first time, I would strongly suggest you get started with Axum. Right. So that's that. Again, my personal opinion. So okay. So let's add Tokio and see how we change this. So so I'm going to go to the terminal, and I'm going to add a library. So this is the first time we are adding a dependency. So cargo add Tokio. So this would add this. And once you add Tokio, you'd find that, hey, it has a bunch of features. So it has bytes, it has file system support, it has full, we'll be using that, but then it has all this stuff. So these are called features in Rust. So all these crates, they expose a certain bit of functionality. Say, for example, if you're only doing network access, you never need to do file system access in your server. Then why pull in the code for file system access? You don't need to, right? So similarly, if you're targeting a WebAssembly runtime or something like that, then you don't need num CPUs. Or if you're running on a microcontroller which has a single core sort of like a thing, then you don't need num CPUs. You don't need that, right? Or you are never going to do process management. You don't need process. So on and so forth. Or if you're not going to handle signals like Control C or SIGKILL or things like that, you don't need signal. So there's a whole bunch of things where you can kind of like cut it down to actually make it smaller. But here, for the sake of learning, we're just going to use full. I think most projects also just throw in full and then they figure that out later. But it's good to know that you can kind of like pick and choose what you want, and we can go from there. So let's add this. So we'll go to cargo toml. And when you add it, it's not there. So we're going to say version equals, and we're going to say features full. Like, see, so there are so many projects using this on GitHub that Copilot basically says, hey, you should use features full. So that's that. So we'll let the Rust analyzer catch up for a second here. And we're going to come here, and we're going to change the main function to say, hey, this is an async function now, right? When you just run this, it basically says main function is not allowed to be async. So this is the compiler error. It's not allowed to be async, right? So this is the error. And so how do we solve this? The way you solve it is basically to say Tokio : me. So we do this, and now this error goes away magically. It's like, what dark magic is this, right? Why does adding this actually make it okay for the Rust compiler to say this is there? Now, this is where the power of macros come in, right? So when you do this, so let me hide this thing and make this bigger. So when you add main, so this is essentially what Tokio main rewrites it as. Basically, it's a normal main, and it actually creates a body which is async. Okay, so this basically returns a future here, and then uh, all it returns is, and then it creates another block where it basically says, hey, Tokio runtime builder, new multi-thread. So that means that it's going to create a multi-thread runtime. It enables everything because we said full and all that. It builds a runtime, and then it basically says, hey, block on this body. So this is, when you say build, it's going to allocate the thread pool. It's going to keep it all ready. It's going to use the number of CPUs to make sure that it has so many threads running and so on and so forth. And it just blocks on the body, right? So to do this. So now let's run this to find out what happens, right? So again, the result is going to be anticlimactic. So it's just going to work as expected. Right. So yeah, and then it says genetics. I know this is a little bit of a step. So any questions here at all? I think it's a good time to pause and ask questions.
No, Vagmi, the last bit. So you made this as a Tokio main function and you ran it. So what did you do? You did pretty much call that function inside by creating a thread pool, huh?
Yes, exactly. So it created a Tokio task. So this is it created a, I wouldn't say it Tokio. It created a future. So this block async return. So let's write this. Okay. So let's write whatever this gives. So let's comment this out. Okay, and then we'll do this. So that we can look at the types and see what happens and so on and so forth.
But it did not start a server, right? I was expecting it to start some web server.
No, it did not. So we are just using Tokio for now, right? So we are not using Axum. Okay.
Oh, okay.
So let's look at what this is. So here we start an async block, and then this implements a future. So this gives me something that will implement a future that will give an output of nothing, right? So this when you have this type, which is like an open parenthesis and a close parenthesis, it basically means it's a unit type, or it has nothing actually. And then we create this builder, which is a multi-thread. So this creates a builder. We enable everything. We build this. So this gives me a result. So this is again one of those error handling things in Rust, where it's either a success or a failure, and you're expected to handle the failure. Here, before you can use this, you have to handle the failure. And the way we use this is that when we do error handling here on expect, right? So it gives us back the runtime. So let's do this. So let's say let RT equals, and we'll put a semicolon here, and we'll see. So this will give me back a runtime. So when you do a build, it's going to give me a result of something or whatever. So it gives me that result. So what Rust expects you to do is that if you have to get to the runtime here, you have to handle the error first. And that the way we handle the error is we say expect, right? So what expect does is that, hey, it should expect that there is no error, but if there is an error, it's going to say message failed to build the runtime and crash the process actually, right? And then it gives this. So that's what expect does. So there are better ways of handling runtime. You can log it, and you can simply not call this, and so on and so forth. But when you go into those workflows, you will never get access to the runtime variable, right? So that's the cool part about Rust. So by the time, if you know you have the runtime variable here, the compiler will guarantee that, hey, this code path will only occur if runtime has been allocated.
Yeah.
If not, it's going to fail. So that's actually a really cool guarantee to have from a compiler, especially when you're doing asynchronous programming. And yeah, for the sake of completion, let's run this, and this should just work. So this is what the code expands to. So there is no magic here. It's just that macros make your life so much easier when you implement it, right? So so with me so far, any further any other questions? Everybody here at this point? Maybe I should check this code in. Yeah. So yeah, it wouldn't be quite this thing if you didn't sleep. So sleep, you get a duration.
But it did print Vagmi. I'm unable to run without any sleep. It is printing Chennai geeks.
Yeah, that's right. So I just want to make sure that we are able to sleep for a while. So this is the whole point of Tokio, is that it doesn't block the threads, right? So I'm going to run 15 and or we'll say 10. Okay. Again, I should have tried this before, but bear with me for a sec. I'm going to watch for cargo. So, okay, I'm going to run this filter just to see how this works. Cargo run. I'm going to, okay, I can't filter this and show. I think I messed up the filter somewhere.
You're trying to show all the, oh, okay, you're trying to show multiple threads running, huh? Because
Yeah, exactly. So
I think, yeah, you can hit T to show the threads, right?
yeah. So I'm just trying to get enough time so that I can like switch between and then show the threads.
Okay.
So I'm waiting for 15 seconds. Cargo run, and this should come up. Hey, come on. Why is this not coming up?
The binary will be the running, right? You will actually not get cargo there, I think.
Yeah. Got it.
Filter by the CG Axum workshop.
Yeah, I think it doesn't show the thread when it's running the filters. But anyway, yeah, I think this is the but the idea is that so you'll get these threads that are running. I should probably have prepared this better. So you'll get the list of threads running, and then you'll be able to say that, hey, this is what it is. These are the number of threads it's running, and so on and so forth. But you get the idea. So it's going to wait for like 5 seconds and then do this. So as you can see, it actually sleeps, and it's not going to block the thread. So it's going to do this. So,
but did it?
Right.
Okay, it blocked, Vagmi. It blocked, and then it printed Hello Chennai geeks, no?
That's right. It blocked. That's the whole point. The point is that it'll block. So this whole thing becomes a block. So if you notice here, what happens is that this is the body that it generates, Tokyo sleep, and then println, and then it blocks on the whole body.
Okay.
Right. So that's how this whole thing works. So if you have to do it another way, then we can println and then we can block it and so on. So, but yeah, in fact, let's do that. So if you want to see that happening, I think it makes sense to. Yes. So we can actually println something before.
Oh, you are spawning a new thread now.
Yeah, I'm joining, doing a task. So I'll say.
Okay, and then you'll complete when both are done.
Yeah. Oh, it's a handle dot.
Finished.
Mm.
Only join or
Handle await.
await.
To do await, you need the runtime.
Yeah, rt.block. Yeah. So this is so let's try running this. So what I'm trying to do here is I'm going to this thread, this task will sleep for 5 seconds. So I'm going to start the task. So this starts right here. So in fact, I'm going to also add a println saying that the task started.
Hmm.
And then it's going to wait 5 times, and then it's going to say hello Chennai geeks. And before that, this should also print. So so the order should be task started. This should print, and then we'll get this thing. So let's see if this works.
Hmm. Okay, this should print came
first, right? So the thing is that you don't control when this
Which
thread
gets
comes.
answered first.
So I'm pretty sure if you run it a couple of times,
Change
it'll change, right? So it's multi-threaded code, and yeah, you have to deal with multi-threaded and IO at this point. But you get the idea. You get the idea of like, okay, what is Tokio doing behind the scenes, right, to do this? And this is extremely powerful, right? So once you understand at this level as to what Tokio does, everything kind of like falls in place from here. So now let's get to the main part. Yeah.
Whole thread management, all these joins, all these green threads is not part of Rust standard runtime or library. It's only by external implementation like Tokio.
Exactly. But what Rust gives you is the definition for future, right? Okay. So it knows what to do with future. It knows that, hey, this is like this thing. And because things are future, it knows, okay, what is safe to send into the future? What is not safe to send in the future? All that kind of stuff. So what Rust gives you is basically guarantees from the compiler on, hey, if you're running asynchronous code or concurrent code, that your memory will not get messed up because of that.
Right? But this is very, that is what. No, but this is very uncommon, right? Meaning, usually programming languages give also a mechanism to start threads, join them, and all. But do you know why?
Yeah. So I think the actual threading library that is built into Rust. So like if you want to do pure thread management, that is there in Rust. So you can use standard thread, whatever, and then you can do all that stuff. Now this is asynchronous runtimes, right? So you have several trade-offs when it comes to these async runtimes. So Go has kind of made a particular trade-off when it kind of scheduling, where say, hey, I want to do cooperative scheduling for these green threads. Now, Elixir basically comes up and say, hey, we are not doing cooperative scheduling, we are doing preemptive scheduling for these threads. Right? So, do this. So these are trade-offs that say the language designers kind of like force upon all the users. Actually, with Rust, you don't have such things. So if you want to use small with preemptive scheduling, you can do that. Or if you want to do Tokio with cooperative scheduling, you can do this. So it's up to you to choose what you want to do, right? So with this, so yeah. So I feel I think this was one of the features that took the longest to stabilize in the language, primarily because of these discussions. To say, hey, what should be in the language and what should be in the implementation, right? And so, and what is the effect that it would have on the community? So would it fragment the community to do this? So even now, I feel they did a really good job, but they did not get it perfect. In a sense that there are libraries which only work with Tokio. There are libraries which only work with async HTML, right? Because of the way they, because of the utilities that are kind of included and all that. Again, there's this refactoring process. I think the community will eventually settle on something. But I feel this is like a step in the right direction. And it is also helping them move other targets. So people talk about generative associated traits and how its impact on async traits. So if you have a trait and that has an async method on it, how do you deal with that? We'll talk a little bit about that as well, and then we go from this. So what I'm going to do is I'm going to check this in with this commented bit. So just so we know, okay, this is there. And I think this is really cool that we had this discussion. So, and others, please feel free to pause anytime. So,
yeah, Vagmi, I have a question. So, yeah. Is the word green thread is right in this context? Because my understanding is in Go language, the Go routines can be called as green thread because there is a M and N mapping. So there is a set of Go routines and there is a set of OS thread where you map and run. But generally, async, you have an event loop, and the event loop is executed by one or more threads. So there is not really another abstraction of thread, green thread, that plays here.
Yes, I think this is where we get into the semantics of colored functions and say, hey, Go does not have colored functions, but this thing has colored functions. Yes, you're right in a sense that they are technically not. I mean, like calling green thread. I mean, there is no like particular definition of green thread, but there is a distinction between the way Go handles its Go routines and the way Rust handles its async kind of await sort of like runtime. Yeah, did someone raise their hand? Or maybe I'll talk and then
go ahead.
Yeah. So the way, the way Go handles it is basically, I mean, it doesn't have this colored function. So as you can say, you can take any normal function and run it on a Go routine, and then that's fine. And you deal with this. But in Rust, they have chosen this sort of like a runtime mode because they needed more compiler support for this event loop. They wanted to make sure that the types that they're sending over are specialized, and they're like sync, send, save, and things like that. And so I think it's sort of like a design choice, and also the constraint of the language that they couldn't do this. But Zig, on the other hand, when its sync implementation comes back, so I think it was in 0.10, we lost it in 0.11, and now it's coming back in 0.12. Like, I'm really waiting for that. But that has a similar model to Go, and there it's like sort of green. I mean, you can call it, again, there is no like a perfect definition of a green thread. So, but it's different.
No,
but what you called out is different.
I mean, the reason why I mean, I'm not able to fit that here is in Go routine you have a stack. So when we say green thread, the thread has a stack apart from the OS thread stack.
Yeah, even here it has a stack. Even here, the async functions will have a stack, actually. Okay, but
they are part of the event loop, right? And the event loop is executed by the OS thread. So basically, that stack is the.
It is not a single thread. It is an MS to N again here. So right. So here you can pause. You can bring it back. So you have the stack for every future. So for a task. So it has its own sort of like a stack, and that is kind of like paused, and you can bring it back. So there is an event loop that is running. Even in Go routine, right? There is a sort of like an I mean, even though it kind of gives an illusion that is paused, there is an event loop that is happening, right? The Go scheduler implements that event loop, and which actually then says, okay, this needs to revive.
No, I wanted to pinpoint. So the technical definition for a green thread is basically who is going to schedule it. If a runtime is scheduling it, then it's a green thread. If OS is scheduling it, it's not a green thread. I mean, that's basically what quantifies what a green thread is. That's why this is a green thread, because Tokio runtime is scheduling it.
Correct.
OS is not scheduling it.
Not an OS level thread, yes.
And similar to Go, there the Go runtime is scheduling. It's just built into the sort of like the Go binary, right? That runtime is kind of built in, and it's also distributed by the compiler.
Okay, thank you.
Cool. So that's that. And then so this is good. So we got this. So now let's add Axum to this. So this is all about Tokio. I think I pushed the code up, so we should be able to run this on Gitpod. Now let's talk about Axum. So I'm going to get this. Oops. Let me add Axum. Cargo add. Axum. Sorry. One of these days, I will learn how to type. Oh.
There is a ChatGPT for that, Vagmi.
Yeah. So basically, and if you see Axum, it automatically comes with a list of features that are enabled. So by default, it's going to give us form, HTTP1 handling, JSON handling, mash path, original URI query. It depends on Tokio. It does tower log, tracing, all that stuff. So which is really cool. So what I'm also going to add is I'm also going to add tracing. And I'm also going to add tracing subscriber. Okay, so I added tracing and tracing subscriber. So this is all good. Okay, and I'm also going to add, yeah, I think this is good for now. So let me add this. So
don't you need to do that feature all in like how you did include all features full?
yeah, you don't need to. So here, that was for Tokyo, but here it already comes with the features that we need. So if you add Axum,
Oh, the plus
it
minus.
pretty much comes with all the features. Yeah, yeah, it already comes with all the features enabled. So this is all we need. And here again, tracing comes with these features, which is good enough for us. We don't have to worry about this. And we have the tracing subscriber as well, which has all these
but
features.
Tokyo does not have anything added by default. It's all minus.
Exactly. It's all minus.
Okay.
And then it forces you to choose. But there is also this one feature that that they have, which basically enables everything, and that's what everybody chooses. Because we are application programmers. So that's that. So now let's start using Tokio, right? So so first, how do you start using Tokio? We start with a TCP listener. So we will say Tokio net TCP listener bind, and we will start an address 0.0.0.0 colon 3333. Some port dot wait dot. So I'm not dealing with error management as yet. So okay, and then I'm also going to create a router. So create a router, and then I'm going to router dot and I'm going to get our greet function. Okay, and I'm just going to go to the greet module. I'm going to turn it into an async function. Probably have to put async before this. And for now, I'm not going to have it take any parameters. I'm just going to just return hello world. Okay. In fact, I'm going to knock this format out. I'm going to say hello world.toString. Okay. So these tests are going to fail now. We'll have to fix that. So now this is an async function. So we can't just test it this way. So right, for example, if you do this, so it'll say, hey, the impl of future output of string doesn't implement debug, right? So I can't do this. I can't test this, right? So so what I'm going to do is I'm going to say this is actually Tokio test, right? And this is also an async function, and I'm going to say greet. This doesn't take any parameters, and this needs to be hello. Right. So with me so far? I'm just going to run this test just to make sure everything is working.
Can you show the main for a moment?
Yeah, one second. Yeah, main, I haven't done this, so but yeah, let's go to main. I'm just gonna, I got it from the wrong place. So. Right, so we have this, so we have to still bind it. So let me do an Axum serve listener. And wrap and also do a so I'm just going to run this just to make sure everything is like running. Mhm. Okay, this should work. So why does it say it's moved here? Yeah, so it basically gives that, and then this I think would actually return self. So you can use it as sort of like a builder pattern here. So now if you do a cargo run, it should work. And let me also make sure it works by going to HTTP host. Yeah, hello world comes. Okay, I know this is a lot, so I'm just going to walk through this once more. So let's start with the greet method. We have turned it into an async method here. So we are doing a pub async fun greet. So before that, for others who want to follow along, I'm just going to check this in. So we have turned it into an async greet method. Okay, so again, nothing fancy here. We have the same greet method, but we have marked it async. We removed the parameter so that it just gives a standard method. And we also want to test it. And the way we test it is that we are going to use the Tokio test macro. Again, if you notice here, it is the same sort of thing, right? So it basically creates this body, and then it does this Tokio runtime for the current thread, and then it basically like locks on this body, right? So so that's the same thing. So it's nothing specific. In fact, before the Tokio test macro, we had to do a Tokio construct this runtime and then also block on it and things like that. So this macro has actually made life a lot easier ever since it came. And then we are basically doing a greet, but here you have to await that call. So when you call greet, so this returns a future, and so when you await it, it basically resolves the future and then gives us that, and it gives us that value. And we are basically asserting that these two values are equal. And then so let's just run this test. Yes, test is passing. Good. And this is a simple function, right? So we just take this and then we return the output. And then we are creating a router. So this is the first thing that when you create this. So you create a router and you say when you go to /, you handle the get with a handler of greet. Okay. So if you notice here, this handler : is basically added by Rust Analyzer, basically because it's the name of the type, and it adds this greet method. and we'll actually see path parameter handling and things like that, and then we'll talk about how this is. But if you see, I'm not dealing with request or response or anything like this here, right? So there is no request here, there is no response here, there are no headers. I'm not doing any of that stuff. I'm just basically asking it to return a string, and then it writes it to the body, right? It knows how to do that. And then I'm creating a listener. This is like a Tokio Net TCP listener, which binds to 3333. And I'm basically saying, hey, serve this router, and I'm calling it into make service. And then it makes this. What this does, like what into make service does, is that we mentioned something about tower, right? So tower basically knows about what a service is and what this thing is and all this. So you're basically taking this router and converting into a tower service, actually, and then you're basically asking the inbuilt Axum HTTP server, which is built on top of Hyper, to listen to this. And Hyper is one of the fastest performing like web servers out there. I think it's on par with like C++'s Drogon or things like that. It's like insanely fast. So and then it basically wraps onto it, and that's where it works. So it starts the server. It basically writes a log message here. In fact, it probably doesn't write the log message. Let's do this cargo run. Yeah, it doesn't write a log message. We need to make sure that it writes, and for that we're going to do a tracing subscriber font in it. So this basically makes sure that it starts listening to events, and then it writes it to the std out. So if you do this now, so it's going to basically say, hey, at this time it started listening on this, and this is the crate which is listening to it, which is our binary, and then this. Any questions? I know this has been a lot, so.
So basically, unwrap gives you the actual object. Vagmi. What does unwrap usually do?
Yeah, unwrap, what it does is that it so this will give a result type. So local address will basically give a result of the socket address, or that could be an error, right? So here we want to debug what is in the socket address. So if it's not able to get to the socket address, it should fail, right? So let's see what happens. So if I run cargo run again, right, it says address panicked. It calls a result.unwrap, result already in use, actually, right? And this is basically where it failed. And if you want to know where exactly it failed, you can run it with
With smileys.
yeah. So let's look at where it failed. So this gives the stack trace of where it failed, and it's in main.rs12. So main.rs12 is basically this. When it started doing this, and it tried to bind to the listener, it basically said, hey, I can't bind this to this listener. This listener is already bound. So here is basically where the unwrap fails.
Cool.
Right. So HTTP. So by the way, people who have not used HTTP, I mean, you should use it. This is amazing. So it basically gives all the headers and things like that, the content type and all that. It's really cool. So, and it's pretty high level compared to like curl for debugging things. Right. Any questions so far? We can greet us with our name. Did I check it in? Oh, Jason. Okay. Let me also add this. Oh, I didn't push it.
Vagmi, does Homebrew have HTTP? How do you install
It's actually HTTP.
HTTP, yeah.
Yeah.
So it's Hebrew install HTTPI.
Oh, HTTPI. Okay.
HTTP. So this is amazing. I mean, I can't recommend this enough. So yeah, it even gets you the stuff like I'm a teapot will give you this. So it's fun. Any questions? How are you guys feeling about the pace?
So, Vagmi, one question. When you
Yes.
had get method separately attached to the router, right? Like when you said router dot route, it didn't work. And now when you find it with in this creation itself, when the instance is created, it's working. So,
Yes.
what difference was it?
Right. So here, what happens is, again, this is basically where you do this. So it says, hey, this move occurs here because it doesn't implement the copy trait, right? So you're trying to, I'm trying to do this. So when I do this route, it's trying to mute it. So I don't know if adding a mute doesn't work. So it basically says that, hey, you used it here, and then you're trying to reuse it here, actually, right? And then you cannot do this. You moved this value here because the route object actually is basically taking self and not in reference to the self. You see what it is? So it consumes it and it returns the inner mute. So I cannot call it this way, and the only way I can call it is basically as this, actually. So, and that was the so it's basically like, okay, whether something takes ampersand self or self as a parameter. Here it takes self as a parameter. That means that it tries to do a copy, but here in this inner mutation, it is fine because you're doing it as a part of the same object and it returns itself. So that is fine. Again, the other thing would have been fine is actually so one second. So if I say let router 2 equals router dot, right, and then I do a router 2 dot into make service, this is perfectly fine. So this will work.
So to put it in a nutshell, see, the route method takes ownership of the memory allocated for router. So then Axum serve cannot take ownership again, right? So it's like basically it's taken ownership by that. So now Axum serve cannot take ownership of that all over again. So for that reason, this works. So which means we've gotten route takes ownership of router and gives back the router 2. And Axum serve can take ownership of router 2.
That's right. So this basically consumes router. Yeah, this consumes router. Calling this method on this router consumes this method and it changes it. So it's not the same anymore, and then it returns something else, actually, right? So like after it is mutated. So you're only supposed to use that and not this. So, and that's what it says. So had this been an ampersand self, it would have worked, actually, right? If the type was ampersand self. But here it's not type ampersand self, but it actually does a mutation. And so we cannot use this here. So, I mean, you can get hints like as to why it consumes it. It's basically an implementation thing. But from a type system perspective, you can know that, hey, this is consumed. And so, this is why there is no ampersand self here. This is self. So it actually consumes this method. You kind of like, and once you see enough, like, enough Rust code, you kind of like build these patterns and say, hey, oh, that's why this doesn't work.
Yeah, but there is no ownership. Sorry, there is no mutation. It is just about ownership.
Yeah, it's just about ownership. No mutation here. Yeah, it's just that it consumes it. So and you moved the value, and how it is handled and implemented internally is basically the library's prerogative. Right?
So had you used to like borrow, would it have worked?
No, it wouldn't have worked. That's why I tried this thing. There's no way to have borrowed it, right? The type system doesn't allow it.
You can't borrow twice, basically, right? Yeah.
Okay.
I think the point to note here is the reason it consumes the router is it returns the router. So it cannot return a router if it doesn't own the router. And I think that's what makes about the ownership.
That's right. That's right. And again, it's a design choice. I mean, it doesn't have to be this way. It's just a design choice. And here, even this into make service basically does the same thing, where it takes a self. The other way to do it is through references. So one of the reasons why many Rust libraries also make these decisions is to remove the idea of lifetimes from this thing, right? Maybe there was another way to have get it done, but it would involve the users of the libraries to deal with lifetimes, actually, right? And so usually library authors try to avoid lifetimes like a plague on their on their public interfaces, and so they try to do this because then they would basically it will not be that usable, right, for new users to come in, and so that's the reason. But I'm pretty sure you can make it work with lifetimes without having to recreate these smaller temporary objects that are there.
Yeah, thank you.
You're welcome.
And
Cool.
Vagmi, does Axum do hot reloading, or we need to do something more for that?
No. There is no hot reloading, none of this stuff. So if you want to do hot reloading, you could do a cargo watch.
Oh, it's a cargo run.
Yeah, and then just it'll basically watch, and then if you change something here at all, yeah, it'll basically like rebuild and do this. So instead of saying hello world, it needs to be hello world 2. So this would basically recompile and run this again. So usually the incremental compilation is pretty fast, but yeah, there's not like Rails or something like that where there's like hot reloading or TypeScript or something. So yeah, it's pretty high level. Okay, now so on to the fun bit. Okay, now what we want to do is we want to add like a path handler to this, right? So where you say hello :name, and then I want it to basically say, hey, this is a name actually, right? So, but I don't want it to be any name. This needs to come basically in the path. Okay, so right, and so this needs to come from Axum extract path, and I'm going to do this. So here I'm now going to do like format hello. Okay, and I'm going to say hello. So let's do this. I'm going to call this path of name. I'm also going to run a test, run the test and make sure it passes. Test. Okay, here I need to make sure I use Axum extract path. Oh, this needs to be a string. Sorry. Okay, so now let's run a cargo test. Oops. Like I said, one of these days I'll learn how to type. It failed. Oh, it expected hello world. No. Hello, Chennai Geeks. And so, yes, this test passed. So here what we did was we basically are saying the handler that, hey, we are expecting something to come in the path called name, and we're going to handle that. And you basically take that and just return a string back. Okay, so it's there, and you can see doing testing in Rust is like really simple, where testing these individual handlers are like really simple actually, as opposed to say controller testing or things like that you would do. So let's go back to main.rs. Here nothing has to change except the route actually, so we'll call it name. So now if I do, let's run this cargo run, and I'll do a HTTP localhost 3 and /geeks. It's going to say hello China geeks. Does this make sense?
Nice. But Vagmi, the parameter, if you go to greeting.rs.
Yes. Let me commit it so that others who may want to follow can do this. Okay. Yeah. Let me go to greet. Yes.
So the parameter is path of string. I mean, you're basically creating a new object in the parameter definition itself, a path.
No, so this is destructuring. So path, so if you look at it, so is struct which has just one member in it of T. So it's just one member. So you can name this anything you want. So if you want to call it
you're extracting from the path object pass the name from it. Okay.
Exactly.
Okay.
Right, it'll work the same way. Right. In fact, let's make this a little bit interesting. Okay. What we are going to also do is we're going to basically pass in the greeting and the name. Okay. So, and then let's go here to greet, and we're going to say path of greet. And then we're going to put the greeting and the name here. Okay, and let's add this. So let's call it let greet equals path of so it should do this. So now let's
You need to add the greet in format.
I'm sorry.
In the format line number, what?
Okay,
got to add greet there.
Oh, yeah, sorry. Right now.
And there's a name clash here. In the test, there's a name clash.
Yeah, there's a name clash. And we'll change this. Okay, all good. Okay, so we have this greeting, and then we have this path, and then we have this, right? So it's there. So let's run this again, and wrong number of paths. Okay. Greeting and name. Maybe I didn't save this.
Go to the greet handler.
Okay. I think it needs to be a tuple. Sorry.
One same path object.
Okay.
See, this is why live coding is amazing. Creating a name. So this makes it easy as well.
It'll just be greet of greeting.
Yeah, great of greeting. Okay. Okay. Okay, I think all the brackets, everything is like this thing. So let's run a cargo test. Okay, this is good. And so we'll run this again.
Run the watch only one.
Yeah, I know, right?
Yes, are you on a call?
Yes, I am. Actually, I'm on the stream too. So you're being seen to the entire world now.
I don't care.
Yeah. It's just my daughter in here. So she's like, I'll be done in like 20 minutes. Okay.
Because you're the woodwork.
Yeah. Yeah.
She's like, I don't care, like my daughter.
Exactly. So okay, let's do this. HTTP. Hello, China geeks. Yeah, this works. Okay, so this is really cool. So it's really cool that we got this multiple string handling and all that. And I had just told, hey, Rust does not allow sort of like a overloading function names, right? Or sort of like doing what do they call it? Variadic params and things like that. But that's exactly what we're doing here. So we are coming here, we are changing this the signature of the function willy-nilly, and it's working, right? So and anytime there is like a dark magic like this that you see, there's only one culprit. Can you guess what it is?
It's a macro.
Exactly. So let me do this. Let me add these two and then used two path params. Right. So there's a macro. So now let's look at what that macro is. So if you see here, it says, hey, get is basically getting a handler here. Right. So this is basically getting a handler. So let's dig a little bit in to do this. Now I'm going to close these so that we can do this. So here, if you see, this itself is a function. Get itself is a function which says, hey, get me a top level handler so that this method basically handles get variable, get this thing, and so on and so forth. Okay. So let's go to get. So top level handler basically gets this function, and it has this get variable. Okay, so this is where it is. So it's going to return a function, right? It's going to return a function that actually does this. Now, this has a handler. Okay, so we need to look at what a handler code looks like. I'm trying to figure out if I can
It was
get
there
to
at the top.
yeah, it's go here.
This one.
Yeah, handler, right? So this is there. Now let's look at the handler type. Okay, so GD. Handler. Okay, I'm just going to go to the definition here. Now, the handler is any function that returns an output that is send static. Okay, it needs to be a callable that will return a future. Okay, and then you would also have this implement a function. So let's see if I can get to. I'm going to reduce my font size for a bit here so that we can get to this. Yeah. Okay. Impl handler. Okay. This is where it is. So basically, it gets many functions for this, for different types, and it has a last type. So for all these types that it returns, so the $ty, okay, all those $ty's should inherit from request parts. And the last one should should implement the from request. So these are two traits which basically say, hey, this path param that we had. So bear with me for 1 second. So this Axum extractor for the path that we have, right? So this type that we have actually inherits from either from request or from request parts. Okay, so this type. So it is actually taking it from the request, and it's going to parse the request from the path, and it's going to put in these values here. Okay, and what this returns, right, for this future should be something that is into response. Does it make sense? So string here, Axum actually implements an into response for a string, which actually makes it so that it returns a 200, and the headers are set as text plain, and the body is the content of it, the UTF-8.
The thing is a little bit, I think, beyond this. If you enable wrapping, we'll actually see the return type mentioned on the left side.
There?
The impl, right? In the impl, that the macro definition. Here, before the where, we are actually losing the fact that they are returning the res. Like, it's like wrapped. Like it's not wrapped.
Oh, it's not wrapped. It's just that it's not.
It's off the screen. We can't see it, right?
No, it is not off the screen. So here,
it must be before. Oh, okay.
Okay, no, that's the thing. So the thing is, now this implements call, actually, right? So this implements call, which is the self future, and self future for this trait is something that returns the into response. Okay, so I'll show you this in 1 second. Okay, so if you look at the self future here, right? So self future is basically dim future whose output is of type response. Is your mind sufficiently blown yet?
Vagmi, you managed to make start Ruby on Rails to advanced Ruby on Rails.
No, yeah. So yes. So again, like I said, there is a method to this madness. So don't worry about it too much. Oops. Don't worry about it too much. So, but all I wanted to show is that there is a method to this madness, right? So even though so there's a lot of work that has gone in to make Axum this simple, actually, right? So if you are working with core Rust, you don't get. I mean, you have to do a lot of work to get to the simplicity that many of the Ruby or Rails or like Node.js or things like that do. But the reason they are able to get to that simplicity is that they sacrifice performance for the ease of use. Okay, Rust is one language where you can have the cake and eat it too, right? And that's why I feel it's like the power of C++ with the expressiveness of Ruby, right? And that's why I love Rust so much, right? Is that it allows me to do this. But don't worry about it. So we have gotten to this point. I just wanted to make sure we are almost like 15 minutes until we close. So what I'm going to do is I'm also going to show JSON handling, and then we're going to stop it from there.
So,
right? So
one quick thing. Yeah, I think it's worth mentioning. Again, all of this is coming at no runtime cost. That's also the kind of beauty, right? I think it's worth mentioning that.
You mean, Dhruva, all this is
the macro thing, right? Like it's that whole thing. There's no runtime cost for that.
Yes. So all this is compiled down. So it's as if you write all those methods by hand in C++ to get there. Right? So it's insanely fast. So what we're going to do now is kind of do like this thing where, say, for example, if you have a list of to-dos, and we want to show them. But in this one case, I just want to take JSON as input and then return the JSON as an output. So we'll do that first. So for doing that, we're going to add a crate, which is going to be called Saturday. And we are also going to call Saturday JSON. Okay, there are going to be two this thing. So Saturday basically stands for serialize and deserialize. JSON basically allows you to do JSON handling. Saturday allows you to do serializing and deserializing. And then we'll see how this is that. So we need one feature here, which is called the derive feature. Okay, we'll talk about derive really quick here. Let me go to cargo.toml and we'll go to Saturday. By the way, when you do a cargo add, you can also say a -f and then like add the feature. But do this. So here I'm going to create a struct for to do, and I'm going to have ID, which is a U32, and then I'll do a title, and also do a completed. Okay. Thank you, Copilot. And then what I'm going to do is I'm going to do a derive debug, okay, and I'm going to do a serialize, and I'm going to also do a do this. Okay, now to create a to do, I'm going to create another struct called create to do, and that will just have the title in it. And here I'm only going to derive debug and serialize. Okay, sorry, debug and deserialize. Okay, to do this. So what these traits allowed me to do is basically I'm adding a few functions here, which will let the Rust crate Saturday take it to a sort of like a serializable form. Okay, and then the format it's going to get serialized, like JSON or YAML or things like that. They are implemented by different crates. Here in this case, we are going to use Saturday JSON for our JSON handling crate. But there's also YAML. There is also RON, which is like the Ruby object notation that's there, or you can do completely like binary formats that's there. So right, all that kind of stuff. So once you are able to get into this abstract serialized format, you can then serialize it down to any format that you want. And this is really cool. And I think this is something that is very unique to Rust. I haven't seen like an implementation of this in other languages, because in all the other languages, serialization and format are kind of like tied to each other. But in Rust, they're kind of like separated, which also means that, say, for example, if you want to transfer an object across a CFFI boundary to something else, right, and that expects it in a certain format, say, for example, message back. So there is you can basically have Saturday message back and then turn it into a message back form, right? So it's actually a really cool way of thinking about serialization. And this is also one of the things that I find when you adopt new technologies, right? You also not only adopt like how the way the language works and things like that, but you also think like fresh ways of solving problems, right? And while you might be tied to a certain way in one language, when you come to another way and be like, that seems reasonable, or that seems like a better way, and then like other languages can copy. So that's why this is really important. So let's create a to do here. So I'm going to basically have a function that will give me a create to do, and that's going to take in. I'm going to completely ignore what this is going to say for a second here. I'm going to say JSON of create to do, basically JSON to do, and this is going to return a JSON of to do. Okay, so basically that's what I'm going to do, and more or less this is what I want. So I just need to make sure that I have the right. Cool, this is done, right? So again, I'm going to do this. I'm going to write a test for this. Right. So wait. Okay, again. Right, so I'm going to do this, and let's run the test just to make sure if this is there. So all it does is that it basically creates. I have one where I do this. So it can't find serialize and deserialize. Let's do this. Use day, deserialize and serialize. I think you don't need pub here. I think it should still work. So I have a title implementation here. Title, it is there. It's just says that it's not used. So once this is used, everything else will be fine. So let's. So what I'm going to do is I'm going to run a cargo test just to make sure everything is fine. Okay, yeah, this works. So let me go to main.rs, and I'm going to add another route here. And this time around, I'm going to say dot route, and I'm going to say /API/todos. So when you post to it, you're going to get. Okay, so I'm going to get these. So from greeting, I'm going to get create to do as well, and I'm going to get the post method here. And I'm going to do a semicolon here.
So you remove, yeah, okay.
Yeah. Right, so this is done. So let me do a cargo run. And this is working. So if I do a HTTP localhost, 3333 API to do's, and I'm going to say title equals learn first. So it's going to give me back a JSON object. So I have posted a JSON object. So with HTTP, this when you do this, this gets serialized into a JSON object, and then it's going to be passed in as content type JSON in there. So when you get it back, I basically set the ID to 1, set the title, and set the completed to false in create to do. So let's go back here for a sec. So here I basically set ID to 1, title is the title, and then we set completed to false, and that's what this gives me. Right. So this way I can serialize and deserialize JSON. So you can see it's actually really powerful. So I don't have to do like a parse of this or things like that, and all that handling. So all that happens, like by default, right? And even when you're testing your handlers, it's pretty high level, right? Really high level tests that you can do here, which makes testing these handlers, actually easy to do, right? To do this. Any questions so far? I know we are just 4 minutes in, and I couldn't get to all of it, but this, we can do a part two, and then maybe on a subsequent Chennai Geeks meeting if you guys want to do it, and then where we can go a little more advanced, and then we can go into database handling, state management, that kind of stuff as well. Any questions? Your thoughts?
Vagmi, quick question. So you did not say this is expecting a type of JSON, but it is inferred because the handler is parameter is JSON RAM. That's how infer.
No, yes. So basically the extractor that we use here, just like how we use the path parameter here, here we are basically saying that, hey, read the body of the request and then serialize it, deserialize it into a create to do. right? So there it expects title as one of the parameters. So basically the title comes up here. I mean, so title is one of the request body items. So that comes up here. And then all it does after is that I want to return this, and I want to return a JSON of to do. All right. So that means that it takes this, serialize it, and then you return it. So that's why we derive serialize on this.
But where are we returning? Okay, create to do is returning the JSON, right?
Yes. Yes.
Okay, and that if you go to main, the function is okay. Whatever this returns, it basically returns that value.
Yeah, that's the beauty of it. It basically just gives a handler, and then here I'm not saying that, hey, you expect a request parameter or a response should be this. No, none of that stuff. All that is in the handler.
Yeah, and the thing is, okay, so the type is JSON, both for the serialization, which extracts from the request body and the response, and then that type also implements like into response and all those things, so that return type will be get processed by the service and then serialized.
Nice.
Again, this is I feel is like the beauty of API design, right? So here it looks magical. It looks absolutely magical that they have this. So it's just this one type implements both the from request, like if you see here, from request, and it also implements into response. So it will also implement into response. Yeah, it will also implement into response for the JSON, the same time.
Awesome.
So that's how it kind of works.
Cool.
So what are your thoughts, guys? So you want to? So are you all ready, excited to go back and rewrite stuff in Rust? Do you work this?
Folks, feel free to speak also. I mean, not necessarily
Yes.
need to chat, but you can also talk.
Yeah.
Definitely, Vagmi. I mean, you just start the fire. Interest to learn, sure. The next opportunity, and see how I can convince my company to use it.
Absolutely, man. Yeah, I meant it in just to rewrite it in Rust. It's just that it's a common trope that that people say, hey, once people learn Rust, they can't wait to rewrite something in Rust. That's one of the reasons. But that said, I think Rust has a place in most companies' tech stacks today. And if not anything, I mean, I think Vercel has been rewriting a lot of stuff in Rust. Their TurboPark is written in Rust. Many of the JavaScript tooling that we use is written in Rust as well. So there is SWC, I think, which Vercel runs as a part of Next, which is called the Speedy Web Compiler. That's written in Rust as well. Yeah, Ram, long time, man, Ramsadan.
Hello.
Yeah, Vignesh.
Yeah, I saw some videos about Rust and Go. So some of them says that Go is easy to learn compared to Rust. So
That's true.
in future, it will be Go or Rust. I'm just
I
starting
think
to
there's a
learn
place.
Rust.
I think there's a place for both. I've done both Go and Rust. I mean, as a programmer, I don't think we should. I mean, those are like really clickbaity YouTube videos or like articles, right? It's also very low effort to produce that kind of a content. But that's it, right? There is a place for both. So there is a place for Rust. There's a place for Go. Go is great, essentially in terms of like, if you want to write a network server and it's a simple language, you can do this. I mean, Go is amazing, right? It works like Kubernetes is written in Go and stuff like that. It's a great language, and the community has taken a lot of efforts in making sure it is secure, it is there. I mean, like the Go's module management and package management system is probably one of the best that's out there. And the amount of effort the Go core team is putting into making sure everything is secure and making sure there is no supply chain attacks and having traceability to it and all that is amazing. And they have been fighting complexity for a long time, right? For example, Rust type system is complicated. I was showing you all the gnarly bits inside on like, hey, this is how we are doing implementing traits. We haven't even talked about lifetimes. Lifetimes is this thing altogether. So Rust is conceptually, I mean, as a programmer, you have to deal with a lot more concepts in Rust that you have to keep it together if you want to understand how the program works. But in Go, things are fairly simple. That means that you can use all that energy and effort to focus on things that are a bit more sort of like in the domain. The complexities could be in the domain. I think Sudhakar and me, we were pairing on a project which was in Go, and we were using a lot of Go routines. It was actually doing SQS processing, but as a part of SQS processing, we had to coordinate multiple tasks on different things, and we had to do like make sure it's rate limited and things like that, and so on and so forth. All that, right? The heavy lifting that we have to do. The language of your choice doesn't matter, whether it's Rust or Go or whatever. It really doesn't matter. At that point in time, you have to you have to deal with, okay, how do we do this? Given the tools that language provides in terms of like in Go, it's channels and Go routines and things like that. How do you build the right abstraction for it for your use case? With Rust, it's a similar choice. Okay, given that you use Tokio or something like that, then how do you build that right kind of abstractions for your use case? So I wouldn't quite go into go with Go versus Rust versus Zig sort of thing. They both have their place and they're both valuable. And I think as a programmer, you should learn as many languages as you can, right? So that you can use the right tool for the right job.
Thank you, sir.
There's only a few things that see, it's still much more easier. Like you do have issues in Go, especially with concurrent programming, which the compiler will not deal with you. Like for example, memory leaks, like shared memory issues and stuff like so. You have to make sure you cover those. Whereas in Rust, the compiler does add. There's some advantage there. But and the other thing I wanted to add, which is very interesting, recently I was doing something with Go. So Go also has added generics.
Right.
This is kind of interesting to see.
Right. Yeah, Go has generics as well. I mean, yeah, Go can, but it also makes it easy to shoot yourself in the foot. For example, Go's map is not concurrency safe. So it is very in fact, we had this bug, this thing. So we had this bug where, the map is not concurrency safe. We forgot to add a mutex on it. And then it does this stuff. Or it's very easy to get a nil pointer when you don't expect it in Go. Go, I mean, you have to be a little more careful when you write Go and be aware of the fact that, these could blow up in your face. With Rust, I mean, sort of, I wouldn't quite say fearless, but you can be rest assured that compiler has your back. But as someone who has your back, compiler also nags quite a bit. So you have to deal with the compiler.
Sometimes it'll be very hard even to understand where this whole borrow checker when it kicks in.
Actually, my problem was not with the borrow checker. Borrow checker is actually, I mean, I guess you have to get over that hump, right? Once you get over that hump, and then you're kind of you will be running a borrow checker in your head at that point, and then it'll be fine. I think where Rust still trips me up is the type system. I feel type system is extremely powerful. At the same time, it is also something that you need to be really careful. So especially when you combine macros and type system and this thing and all that, sometimes it's very hard to keep it all in your head. And you really need the IDE support. Even now, I think I really need the IDE support to go debug this a little further and then do this. Fortunately, you kind of learn tricks along the way to say, hey, is this what it is? Can I write a small test here just to assert, or write a small expression to do this? And what I found after working with Rust is that I started writing a lot more smaller tests. Right, so if I want to make a GraphQL call or things like that, I just write it right there. And then write that as a test for me to explore, and then go from there rather than do this. So,
Nice. Awesome. So that was a great session, both Dhruva and Vagmi. So definitely it was very interesting for us to get also not just the basics, but also jump in and try to understand and see, at least look under the hood. Even though I think I at least did not get all of it, but yes, it's a good start. Yeah, and so the feedback, I've added a form link, Google Forms link in the chat. Please, I think we started with some 25 odd members, but we are like with now 9 members now, which is still fine. So please put your feedback there so that we'll know whether we wanted to go more on like this remote Chennai Geeks meetings or have it in on-prem in some office place. But yes, if we do that, Vagmi, Dhruva, these folks are not in Chennai, so they cannot be there. But I think we wanted to do hybrid. We'll see how it goes. But yes, please give your feedback, and then we'll see how will we plan the next Chennai gigs.
Also, the Sudhakar woke me up really early for this call. So it was like at 6:30. He called me. He pinged me and said, "Hey, Vagmi, ready?" I was like, "What? I thought mine was at 7:30." Yeah.
Ram, it's okay. You can show your face. Like Vagmi and Dhruva will be happy.
Yeah.
So we met Ram also in the last meeting. I think he was talking about you guys all, like, hey, what are you guys doing?
Nice. Hey, Ram.
Hi, Vagmi. It's been a long time. How are you?
Yeah, it's been a really long time.
Yeah.
All right, folks. I really have to bounce. So I have a couple of minutes here. So, but it was really a lot of fun. Yeah, a lot of fun being back in Chennai Geeks, and thanks for arranging this virtually, because I always felt, hey, we don't have that community. We built a community there and all this. But yeah, thanks for inviting me back.
Thank you, everyone. And yeah, we'll continue offline in our Discord channel if there is anything, and we'll discuss there also. Okay.
Thanks. See you then. Bye.
Thanks, everyone. Bye-bye.